Good day, everyone, and welcome to Physics Base Camp. I'm Zane, and this video regards two of the most fundamental things you will ever have to understand in physics: units and quantities. This video is a great place to start if you haven't really been introduced to physics yet, as I will be explaining the very basics of what you should know to understand nearly every other topic within physics. Though, of course, there are a number of additional videos, also about units and quantities, which explain even more individual parts of them. These topics are what you see on your screen, and they are again covered in separate videos, though I highly encourage everyone to watch them as well, since they explain other fundamental parts of what is explained today. Nonetheless, today, you should get a core understanding of what units and quantities actually are, additionally covering how we represent them, and SI and derived versions, setting you on a perfect path to comprehend future videos and ideas. If you have any questions about virtually anything mentioned, or even not mentioned in the video, ask them below in the comments, where I will always answer as many questions as I can, clearing things up or pointing you in a direction where you can easily find your answer. If you find this video helpful or interesting, feel free to leave a like and subscribe. It is very much appreciated and helps support the channel. That said though, let's take a look at some of the pure fundamentals of physics. So, let's start off with the basics of the basics. What exactly are quantities and units? Well, in physics, we have a great number of different subjects, obviously, and in these subjects, we have a number of values that can influence scenarios. For example, if you are looking at a problem about movement, speed is a value that might be important in that scenario, since speed is a value closely tied with movement. These values that carry importance are known as quantities, and to be a quantity, we really just have to be able to numerically measure them. For example, time is a quantity because it can be measured in seconds. We have to be able to use numbers or something to measure that quantity. So if you can think of something you numerically measure, it's probably a quantity. There are tons upon tons of quantities in physics, and the word quantity itself is really just a fancy word for a specific value in a scenario. These quantities are the things we measure and make into formulas, so that with certain quantities, we can find other quantities that may not have been given, such as finding how long a scenario took based on how far an object went and how fast it was going. In that scenario, we'd have three quantities: time, distance, and speed. We could then use formulas to solve for what we want using algebra. This idea of solving for quantities is really the heart of physics, and it helps us understand the world around us, though specifically solving for a quantity is the thing mentioned in a separate video, because that is a different idea in itself. Thus, to recap, a quantity is a measurable value in physics that we use to find other such values in a scenario. The thing is, in physics, we have so many different quantities that it would be rather ridiculous to assign numbers to them without any context. Because remember, we measure our quantities. And so, the real question here is, why can't we just measure them with numbers and leave it at that? Because hint hint, we do in fact need to use something else to measure any given quantity, not just numbers. So what is this new thing, and why do we need it? Well, to understand this, let's look at an example. If I asked how far you walked today, and you said 5, you said you walked 5, how would I know what that meant? 5 meters? 5 miles? 5 inches? It wouldn't make very much sense, which is why we have units, things to measure our quantities in, so we can all properly measure things in the world around us without getting confused. You've probably already used units without knowing it. For example, if you said, this object is 5 inches long, inches would be our unit, where it would measure the quantity length. As you may have already noticed, we place our unit, the name of our unit, we place this thing we measure our quantities in after the numeric value of a quantity, or in simple terms, after the number of the quantity you measured. Thus, a unit is just what we measure our quantities in, and a quantity is simply a measurable value. Now, everything just said can be quite a bit to process for some. So, let's take a moment and briefly list the key takeaways of what we've learned so far, and then come back and take a look at some examples. First, what is a quantity? A quantity is something in physics that we can measure. Again, it is a certain value that we can use numbers to measure. There are many different quantities in physics, but they are all measurable values. And now, what is a unit? A unit is what we measure our quantities in. We measure our quantities in numbers, but also in units, because our units tell us what we are measuring in. A quick final bullet is we remember that we always place our unit directly after the number value of a quantity. And so, let's take all of these facts together and look at some examples so far, beginning with the quantity length. Length is a quantity because we can measure it. We always say things are this amount long, or this short, or this tall, and in each of those cases, we are measuring length. Thus, length is a quantity because it is a value we can measure. We remember, all something really needs to be a quantity is that it simply needs to be a measurable value, a description that length fits. Speaking of measurement, length can be measured in units like inches, miles, or meters, and other such things, because these are all units of length. All of these units measure how long, or how short, or even how high something is, and thus they can apply to length. So, an example of length could be, my house is 19 feet long. We see the word long tells us our quantity is length, whereas feet is our unit. We see that the unit itself was written right after the number 19, which we recall is where we place our unit, after the numeric value. Okay, let's look at another example. Time. Time is a quantity, because we can measure it. We measure time all the time, on clocks, by counting, and in all sorts of other ways. Thus, we can consider time to be a quantity, because it is a measurable value. Basically, it fits the definition of a quantity. Its unit could be things like seconds, minutes, hours, etc., because these are all units of time. They all measure how long something took, and thus can function as a unit of time. So, an example of this could be, the drive took 14 hours, where we see the word took hints at the quantity time, and hours is the unit in this scenario. This makes sense, because we see hours is displayed after the 14, after the numeric value in this scenario. So, these two main examples show what we have learned so far in this video, by showing examples of two very famous quantities and their units, as well as showing the placement of these units with numeric examples. Now, the next thing we'll be looking at is just a relatively simple fact that is quite important to know. Each quantity is measured in one specific unit. That's right, every quantity in physics always has one specific unit associated with it. That is known as its SI unit. We always measure a quantity in its SI unit. So, wait a minute. What about all the other units we can measure a quantity in? For instance, time. Time can be measured in seconds, hours, minutes, days, weeks. How is there only one specific unit for time in physics? Well, that's where things can get a bit tricky. While there are many units that we can measure a quantity in, our goal in physics is to always convert all the other units we might come across into a quantity's SI unit instead. So that might sound a bit complicated, but I assure you it is not. To explain more, let's look at time again. We see it can be measured in all these different things, and yet, out of all these, we always like to measure time in seconds. So if you're ever measuring amounts of time, you'd want to do it in seconds, because seconds is the SI unit for time. Seconds is the one unit we measure time in. In the case that you have time not measured in seconds, you just want to convert that time into seconds. You want to convert those other units into the SI unit. So if we had 1 minute, instead of writing 1 minute, we'd write 60 seconds, because seconds is the SI unit, not minutes, even though 1 minute and 60 seconds mean the exact same thing. This idea of converting a unit, though, is another concept that I will of course talk about in a separate video. Let's look at one more example now. Length. We can measure length in many ways. We can measure it in inches, feet, meters, miles, and many more things. And yet, the one SI unit for length in physics is meters. So we always want to measure length in meters. And if we find length measured in a different way, we would then convert that into meters, because we use meters as the SI unit for length, nothing else. So basically, for now, all I've said is that each quantity has one unit we should measure it in, its SI unit, and when we see it measured in another way, we convert it into the SI unit, because again, each quantity is paired with one specific unit. As always, feel free to pause the video and rewatch if you find it necessary. So, this brings up a new question. Why do we want to stick to one unit per quantity? Why do we have SI units in the first place? I said that each quantity in physics has one unit it is measured in, but why is this the case? While I could just let you memorize this fact, I personally like to explain the why in things, because I find things easier to remember when they make sense. Thus, let me explain to you why we measure each quantity with just one unit. If everyone could measure quantities in whatever unit they wanted, we'd have thousands of physicists running around measuring things in different ways, and it would all just become way too complicated, because everyone was measuring the same things in different ways. It makes sense, doesn't it? By saying, hey, we measure length in meters, we measure time in seconds, and so on, we get this one system, this one standard system throughout the whole world of physics, where physicists all measure things in the same way and can communicate in this shared language. This shared system makes things so much simpler and helps avoid tons of confusion and chaos, also allowing the formulas we use in physics to work properly. And guess what? This system of quantities and units and the many things with them, is known as the International System of Units, or SI units, and it's the system that gives each quantity its one SI unit. Don't get too confused by the name though. That's just the name of our standard system across the world that displays all of our quantities and the units we use with those quantities. So, while this section may have sounded a bit complicated at first, all I really said was that each quantity is paired with one unit known as its SI unit. We always measure a quantity with this unit, and if we see a quantity being measured in a different unit, we convert that different unit into its SI unit. This system allows everyone to communicate using the same units, and avoids confusion, and is known as the International System of Units. Now that we have these definitions down, let's continue with how we represent units and quantities. The example I will be using throughout this section is our old friend from before, time. Though, this is not meant to teach you about time itself. Time is just the example I'm using. So far, you can think of it as if we've learned two parts. We've learned the quantity and the unit. In this example, the quantity is time, and the unit is seconds. However, there are also two other pretty simple parts: the way to represent a quantity and the way to represent a unit. Each quantity is represented with a letter or symbol. For time, that letter is the lowercase letter t. Lowercase t represents the quantity time. This letter or symbol that represents a quantity is known as a quantity's dimensional symbol. So we can say lowercase letter t is the dimensional symbol of time. Now, where does this dimensional symbol represent a quantity? We know it represents it, but where does it represent it? Well, one place is in formulas. We remember from the very beginning of the video that I said we can use quantities to find other quantities in a scenario using algebra. So if, for example, I had a hypothetical formula that said x plus y equals t, we would know that lowercase t represents the quantity time. And so this formula tells us that x plus y is always going to be equal to the quantity time, because lowercase t is the dimensional symbol of time. So we have the quantity, the dimensional symbol to represent that quantity, and we have the unit. But what do we use to represent a unit? Well, it goes along the same lines as the dimensional symbol. We can use a symbol or letter to represent a unit, but instead, this kind of symbol is known as the unit symbol, because of course it represents units, not quantities. Now, like the dimensional symbol, where can we use this unit symbol? Well, do you remember how I said the unit goes after the numeric value of a quantity? Well, instead of writing out the whole unit after that numeric value, you can instead just put the unit symbol. So, for time, the unit symbol is S, because it represents the unit seconds. So in physics, we might say 10 seconds, or we might just write 10s, because both tell us the same thing. We have 10 units of time. So essentially, the unit symbol can just replace where we write out the whole unit. They mean the same thing. So, to briefly review this, we have a dimensional symbol to represent quantities, and a unit symbol to represent units. We might use this dimensional symbol to represent a quantity in a formula, and we might use the unit symbol to represent a unit wherever we might write out the whole unit name. So now we know quite a bit. We know what units and quantities are, we know where to put them, how many units a quantity has, and even how to represent both a unit and quantity with a dimensional and unit symbol. We are nearly done covering the basics of both units and quantities at this point, but there still is a small bit left to cover. Before, I mentioned that each quantity has only one unit, to avoid confusion, and I said the system is known as the International System of Units, SI units. This system covers all units and quantities, and yet, all these quantities and their units can be split into two categories. There are SI base units and derived units. SI base units and quantities are the 7 fundamental units and quantities of physics. Again, there are 7 of these base units and quantities, and they are the most fundamental ones used throughout physics. Derived units and quantities are more complicated units and quantities that build on these 7 fundamental ones, and they cover everything besides these 7. And yet, all of them, both base units and derived units, follow the principles I previously explained. They all have a quantity and unit name, a dimensional symbol, and a unit symbol. On your screen right now, you should see a table that has all 7 base units, and such information about them. You do not have to know what they all mean. Just know that those 7 quantities and units are the most fundamental ones in physics, and they are again known as SI base units. Before we move on to the last section in this video, to review, we just learned that the system of SI units can be broken down into SI base units, the 7 fundamental ones, and derived units, ones that are built from the fundamental 7. And the table on your screen displays the information about the 7 base units, though you do not have to know them just yet. Now, to finish off the video, I'd like to mention 2 general vocabulary words regarding units and quantities that you should be familiar with in order to understand future videos. The first is magnitude. Do you remember how in many instances throughout the video, I mentioned the numeric value of a quantity? Like, for example, the 5 in 5 seconds or the 10 in 10 meters? Well, those numbers are the magnitudes of the quantities they measure. The magnitude is just how much of a quantity there is, though we do still have to say the unit. The magnitude wouldn't just be 5, it would be 5 seconds or 5 meters, etc. This magnitude changes per situation, obviously, as in one situation, for example, the time of a scenario might be 20 seconds, or in another it might be 15 seconds, and so on. Thus, magnitude is just how much of a quantity there is. The second vocabulary word is constant. When a quantity is constant, that just means in that scenario, it does not change. For example, if an object had a constant speed, this means in that situation, the speed would always stay the same. The object would always stay at the same speed, because constant means not changing. Okay, so that is the very basics of units and quantities within physics. Knowing this and understanding it, you should be able to now move on to a number of other ideas similar to this. These ideas include, but are not limited to, unit prefixes in scientific notation, unit simplification, solving for quantities, which I mentioned quite a few times in the video, subsets of quantities, and more. And so, as we draw into the end of the video, I do hope you learned what exactly units and quantities are, how we represent them, and understand the idea of having SI units in such a standard system. Units and quantities are the most important ideas in physics, and once again, I encourage you to check out some of my other videos on these topics, as I will be posting more and more physics content as the days go by. Feel free to leave a like if you learned something, or leave a comment if you have any questions or feedback. I'd love to hear both. So that said, thank you for watching Physics Base Camp, and have a wonderful, wonderful day.